Welcome to the next part in this computer graphics series. This time around I would like to explain and demonstrate the metal shader pipeline. And before jumping straight into the implementation, I will first talk about the general concepts. More specifically, I want to answer the following three questions. The first question is, what is even a shader? The second is, why is it called a shader? And the third is, what is a graphics pipeline? So what is a shader? In principle, a shader is a normal program just like any other, but it is not running on the CPU of your computer system, but rather on the graphics card, the GPU. Everything we did until this point, the window, the application loop, the constant frame rate, is running on the CPU side of things. That also means our program is compiled for the CPU and not the GPU. A shader program written in Metal or the OpenGL shading language needs to be compiled specifically for the GPU. Now, why are these programs called shaders? Well, the name comes from the purpose. In the beginning, shaders were used to calculate light and shadow effects for 3D objects. On modern GPUs, however, shaders are used for far more than just light calculations. Among things like physics simulation, particle systems, procedural generation of geometry, post-processing and many others, most notably modern GPUs with shaders are used to train and execute machine learning models. A shader pipeline or a graphics pipeline is a series of steps, either fixed or functional in the sense that you can replace these steps with your own programs, the shaders, to produce the desired results. The graphics pipeline we are going to use in this computer graphics series has 5 stages. The first is the input stage, which feeds the pipeline with the geometry data, images, textures, and everything else which is needed to produce the output. The vertex stage runs our own vertex shader, which converts every single 3D point from our geometry into normalized device coordinates. The job of the rasterization stage is to figure out which pixels on the screen are covered by the geometry we have sent in. Unlike the vertex stage before, this stage is a so-called fixed function stage and can't be changed programmatically. This is completely implemented in hardware. The next stage, the fragment stage, calls our fragment shader for every single visible pixel on the screen to determine its output color. The last step is to output everything from the fragment shader and from whatever might have been still in the frame buffer to the screen buffer, and then show it on the screen. With the theory out of the way, let's now start implementing things, and I will kick this off with implementing a library holding our vertex and fragment shader. As mentioned earlier, our shaders are basically their own programs and they are written in their own file, so this is exactly what I'm doing here. So we are going to read in a file containing the shader source code and making sure that we also catch any errors in case the path or something is wrong. In order to catch errors either from reading in the file or from compile errors, I'm creating this small helper function which will print out the exact details of what error happened. With the shader source string holding now the source code of our metal shader, We are now creating the library with source. There are other options as well, but this will allow us to change this shader source at runtime and just reload the whole thing without recompiling anything. This error check here would reveal compile errors in our shader source. So that's why this the second time we call this check error function is really important. And here we now really call the create shader function in our construction method of the main renderer. And since we have not done this yet, we are now creating the actual shader file itself, which has the file extension .metal. For us, that's not super important, but if you at some point decide to use Xcode, Xcode will pick up on that and give you other options as well. The metal shading language is C-like. That means we start this off by including the metal standard library and saying that we want to use the metal namespace. And now we will implement like stubs for our vertex shader and the fragment shader in the same file. As mentioned previously, the vertex shader receives 3D geometry data, in this case in the form of vertex input, struct we will define in a brief moment, and outputs normalized device coordinate vertices. And the fragment shader receives vertex output data for every single pixel and produces a color value, in this case green. So now here I'm writing the structs for our input and output containers with the outline of our shader implemented. We will try to build, and of course a typo. So let's see, this now seems to work. Briefly check if the program is still running. And all right, it still works, but we got an error message from our compile step indicating that we missed something. So our vertex output struct is expected to have a position. So we will add this and also mark it up with this position flag, but in the end, same is true for the input. So the input also needs markup so that these structs can be matched to what we will configure in our renderer. And with this set up correctly, we got no errors when we ran the program again. So now we will create another file. This one is for the application. And here we will basically duplicate the structs we just defined in our shader, because we need the exact same types on the CPU side as well, so that we can create these data points on the CPU side and then feed them into the graphics pipeline via buffers. Before implementing the vertex input and output structures, I make my life a little bit easier and use pre-existing types for vectors here. So these type defs just save a little bit of typing when we are on the actual code. So the first is a 2-element vector, then a 3-element vector, and this is a 4-element vector. Same for 2 types of matrices, 3x3 and 4x4. For some extra convenience, I will do the same for the float and double types. So type defs for 32 and 64-bit floating point values. And now I will just include them in the main and renderer file. The next step is to define an exact duplicate or twin of the vertex input struct we defined in our shader. We don't need to define the vertex output struct, since this is only used inside of the shader pipeline. And another structure here for a projection matrix. This one will be used to map our, let's say, real-world coordinates into the normalized device coordinates of the screen. Since we will use the uniform data struct in the shader as well, it needs to be defined here as well. So again, 4x4 projection matrix, and now we will start creating our geometry. In terms of the geometry, I want to create a full screen rectangle with the upper left corner resembling 0, 0 on the screen. Here I just create the member variable holding the 4 points, and in our create geometry function I first make a small comment explaining what kind of geometry I want to achieve. So we have 4 points, A, B, C and D, with D in the upper left corner. Now I'm going ahead defining the 4 points. A is 0 on the x and 500 on the y-axis. B is 500, 500. C is 500 on the x-axis and 0 on the y. And D, as mentioned earlier, is 0, 0. Since our graphics pipeline cannot really deal with rectangles, but rather with triangles, we need to split the rectangle up into 2 triangles. So the first one will be ABC, and the second will be CDA. With Metal, the way to pass the geometry data to the graphics pipeline is to use buffer objects. So for our rectangle, we now need to create a rectangle buffer, and I will also go ahead right now and create a buffer for our uniform. At this point, I realized that I had only created space for 1 point, so now we have an array of 6 points. And yeah, I create the stub for the create uniform function, otherwise the build fails. And now I'm going ahead and create a new buffer so that we can pass in our geometry to the input stage. The MTL resource cache mode is just a way to tell the system how to handle the data inside of the cache on the CPU side. Now that the geometry is defined and copied over into our buffer, the last part of our input is the projection matrix. So the next couple of lines define the rows of a 4x4 matrix and create one using the SIMD functions I already mentioned when we defined the types. So here we can create a new matrix from rows for the projection. Similar to the geometry, the uniform projection matrix also needs to be copied over into a buffer so that we can pass it to the graphics pipeline. Now, with all the necessary inputs defined and copied into buffers, we call the respective functions to create them, and then we need to configure the pipeline. The way to do this in Metal is to create a pipeline state object, and this will do a couple of things. One is to specify which functions from our shader library will be used for the vertex and fragment stage, and the other part is to specify and define how our input data is structured. The render descriptor has fields for the vertex function and the fragment function, So we can specify what the exact names of our functions in the shader we wrote are. And another thing which needs to be specified is what format our color attachment, like the frame buffer, has. Next up, we need a vertex descriptor describing the exact format of all the fields we have in our vertex input struct. So with the next couple of lines, we will tell it that the position field is a 3-element vector and that our UV coordinates are a 2-element float vector. The next field in the vertex descriptor tells the system in which of the buffers it expects this data. And the last one is the offset. So that's just the size of our vertex input and the position field, and the same is true for the UV coordinate. Finally, we define a layout where we tell the system how far it is from one vertex input to the next and which step function our vertex shader needs. And we want the vertex shader to receive every single vertex we defined, so per vertex. And yeah, now we are finished with the vertex description, pass this into the render descriptor, and with the render descriptor we can now finally create a render state which then will be used when we actually start rendering frames. So this should be it for the render pipeline. And yeah, there's again a small error, but now it compiles. And with that done and adding the call here as well, we have one thing left before we can really start to implement the draw call itself. Unfortunately, this last thing involves some math. So yeah, we have already set up the projection matrix, but we have not really filled it with the correct values. And since deriving the correct values is a bit of a hassle and a bit too long for this video, I have provided a markdown document which explains exactly how these values can be calculated. So I just copied this out of the markdown and will now put them into our projection matrix so that hopefully when everything is correct, the pixels from our rectangle are mapped correctly to the window. In our shader, there is one last thing missing, and that is specifying that there is a second input. So now we pass in the uniform, which holds the projection matrix, and then inside of the function, we will use the projection matrix, multiply it with the position coming in, and the output is then a normalized device coordinate. Now that everything is in place, we can get rid of our statics here and in our draw call use all the elements we have created. So the first one is the render state. Now we set the vertex buffer, send in our rectangle. The second buffer is going to be the uniform with the projection matrix. And last but not least, we call draw primitives with the type of triangle and say, hey, this has 6 vertices, 2 triangles, and this should do. So it compiles, but obviously there is another error in our shader. So trying to figure this out, and yeah, we just missed the comma. So now it works. Now we have a working shader pipeline producing only a single output, green. But yeah, good enough. Hope you liked the video, and until next time.